Hi everyone, we're going to look at capacitors that are arranged in a series and capacitors that are arranged in a parallel combination, just like we did with resistors. So to start us off, we're going to look at this simulation here. The simulation has a battery. Its battery is hooked up to a capacitor. I'm going to take a look then when I move this up at what happens. Of course, it gets charged. And we know that the amount of charge that it has on the top plate is always going to be equal to the amount of charge it has on the bottom plate, just due to symmetry. So that's something we can take to the bank as always true. We're always going to be polarizing the top and the bottom with the same amount in a capacitor. So what happens if we then add a second capacitor in a series? So now we have two in a row, just like we would do with resistors in a series, but these are capacitors. So same logic is followed here, where the positive side of the battery is going to populate this first plate that it sees here on the first capacitor with some charge Q. In this case, it's a positive, right? Negative side of the battery is going to populate the first plate it comes to with a negative Q, and those need to be the same Q. So if that's the negative Q and this is the positive Q of the same magnitude, then we're going to have polarization that's going to occur where the other plate here is going to be a positive Q. Again, these plates have to have the same charge. And then likewise over here with the positive charge on this plate, it's going to populate then and pull negative Q to this plate, and these need to have the same charge. And so we have the same Q on each of these four plates. Let's see what happens if we increase one of the capacitors. If we think about what would happen if I increase the capacitor 1's capacitance, its C value, if I were to do that, let's say I were to bring them closer together. So if I were to make the spacing closer just for this one, what would that change about the charge? So I was just saying that the amount of charge that's sent to one and the amount of charge that's sent to the other needs to be the same amount of Q. So if you look at those positive signs there and the negative signs here, and I increase this, it does increase the charge that we have. If you look now at the bottom plate, I'm going to go back to what it was. You can see here it's 3, 3, and 3. If I increase it, look what happens to the negative signs on that bottom plate. That also gets bigger. So it still holds true even if we have unequal capacitors that are in a series. The same charge that's sent out to the one side is the same as the negative charge that's sent out to the other. That means that the charge on these plates, Q, are going to be the same for the capacitors that are in a series. If we were to do this for 3 in a series, I'm going to go back to original here. Let's reset all. And I go to 3 in a series. You can see here that there's 3 negatives, so 6 total negatives. Here you get 3 and 3 positives, so 6 total. If I just change one of these, now there's 6 here and there's 6 here. I can change some of these and make that. It does not matter. The same charge that's sent to this first plate is equal to the negative charge that's sent to the other plate, which means that these in a series all have to have the same Q on each plate. Same magnitude of Q. So let's draw out like what that means about, let's say, loop rule, right, as we look at these. We're going to do that mathematically. But before we do that, let's draw what that would look like conceptually. Let's go back to 2. I'm going to reset all actually, and let's go back to just 2 in a series. If I go to the voltmeter here, my positive and negative red and black leads here, and I populate these, then it would make sense that the voltage across C1, 0.75, you see my total volts is 1.5. That means they each should have 0.75. They're sharing, of course, the 1.5 of the battery. Plus 1.5, minus 0.5, minus 0.75, minus another 0.75 is 0. If I increase this capacitance, then how does that affect it? Loop rule should still be maintained, but if I change this, Q has to stay the same. If I change C, then we have to think, right? So if you change C and Q has to stay the same, then that's going to make the voltage smaller. Bigger C, smaller V. So if it's only 0.375 in this bottom one, loop rule still has to be maintained at all times, and that means the difference between 1.5 and our 3.75 is what we should see across this one. And you can see then that this one adjusts. And it adjusts because the charge does change on these plates, but all the plates still have to maintain the same charge. Let's take a look at this mathematically. So we're going to be using the claims that the same Q, multiple capacitors in a series, are going to polarize, inducing the same charge on each of those plates, regardless of the capacitances that we have. So we're going to use that as a premise for us to do the math here. And different voltages can exist, but loop rule needs to be maintained. That is a fundamental conservation law to circuits that we need to do. Remember, loop rule is one of the most important and primary circuit laws that we can use. It's Kirchhoff's first law. All right, so since they have different C's potentially, but the same charge, we just showed that they may have different voltages. So let's take a look, and we're going to do 3 capacitors here. Now I have the equation here that we have. So I just did a little adjusting there so we can see the screen better. So in this case, I'm going to draw my circuit. So the circuit's going to be a battery, and we're going to have that go to a capacitor here, which we can draw as 2 parallel lines. Kind of looks like a battery, but there's both the same length. And that is going to then go to another one. So we're going to draw 3 of these. Oops. And back to the battery. Okay, so these can have different capacitances. C1, for example, they can have C2 and C3. So they can have different capacitances, and we'll just call the battery voltage V. That was like the 1.5 volts on the battery. So as we said, when the battery's hooked up, it's going to immediately start to populate these. So you're going to have a positive charge here, and we're going to have a negative charge here. And the battery's going to send the same amount of charge. It's positive and the same amount of charge that's negative to these plates. That's going to mean that the charge on the other side is going to have to always be the same between the plates and the capacitor, which would mean if we work through this, we would have the same Q on all of the plates. So if we apply loop rule to this, because now we're going to bring in the voltages, then the voltage of the battery minus the voltage across C1 minus the voltage across C2 minus the voltage across C3 should equal 0. Now, applying this concept that we know for voltages across capacitor as being C equals Q over V, so the voltage across capacitor is equal to Q over C. Then we can substitute out the voltage across each of these capacitors and substitute in Q. So the idea here would be we have the total charge that the battery sent out over the equivalent capacitance. That would be for like the entire circuit. That same charge is going to go to C1. That same charge goes to C2, and that same charge is going to go across C3. So since the charge all divide out, then we are left with the expression that is the exact same expression we saw for resistors that are in parallel. So it's actually the opposite. It kind of feels like a memorization thing, but it is true that the equation for capacitors that are in a series follows the same mathematical format as the equivalent resistors that are in parallel. So series capacitors mathematically have the same equation as resistors in parallel, and we just showed why. All right, we're going to take the same logic and try and approach then capacitors in parallel and derive that. So capacitors that are in parallel, we're going to go back to our simulation here. And I'm going to arrange now 2 in parallel to start us off. So as soon as I move this up, there's going to be charge that's sent from the positive side and negative side. We'll start with the positive. So the positive side of the battery is going to send positive charges to both C1 and C2. Those do not have to be the same charge now, right? Because this is just going to populate it until what? So what's going to dictate how much charge this gets? And if we think about it, it's actually loop rule, right? The loop rule is going to tell us, because loop rule always dominates, and loop rule will tell us that the voltage across these have to always be the same, right? So if I did a voltage across here, that has to be 1.5. The voltage across here has to be 1.5. So in that case, then, we realize with loop rule dominating that the amount of charge we have really depends just on the voltage of the capacitor getting to the amount it needs, meaning the battery is going to drive the voltage across the capacitor to be 1.5. If I have a higher capacity to hold charge, then I can put more charges on there to reach that 1.5 volts. You could think of this as being really just a gradient issue, right? If we have no charges on these, and I have a battery that's 1.5, it's going to immediately spill some of these charges over until there's equilibrium between the battery, the capacitor 1, and capacitor 2. They all have to have the same volts. If there's uneven volts, then there's going to be flow from one plate to another. For example, if I move this, you can see the arrows that are saying that there's going to be flow back to the battery to discharge some of that away. Okay, so number one premise would be that we have loop rule that dominates. And the loop rule is going to say that two things in parallel, two capacitors in parallel, are going to have the same voltage. That's just loop rule, right? If we follow a loop over here, they have to have the same voltages. That means that if they have different capacitance values, but the same voltage, then the charge is going to be unequal, right? The charge is going to depend on the capacitance because the voltage has to be the same. So this is different than what we did in series, where the charges were all the same, and the voltages could be different. Now the voltages have to be the same, and the charges can be different, so it's a little backwards with that. So let's take a look here. So capacitors in parallel, we said, are going to have the same voltage according to loop rule, but they're going to have different charges depending on their relative C values to each other. So let's go ahead and draw a parallel circuit. So I have my battery, and I'm going to do 3 capacitors in parallel. So there's going to be one capacitor here at the draw, then straight line, one capacitor here, and doing it at different distances or spacing so that you can just see that there are different capacitance values. Okay, and we would have then C1, C2, and C3, and we'd have the voltage, of course, across the battery. So now if I show how these populate, I can just make up some amount of positive signs to use here. Same amount of negative signs have to be on the other side. So they have different charges. So one thing we know for sure is that the total charge that's sent from the battery is going to add up to these total charges that it had to populate all 3 of these, meaning this has to add up to Q1, Q2, and Q3, right? The total charge that's sent from the battery is going to be distributed between the three capacitors. Now these are going to be different Qs, right? That's why Q1, Q2, and Q3. And that's what it's saying right here. But according to loop rule, we're going to have the same voltages. So we're going to use the same idea here where we know that Q is equal to C times the voltage of the capacitor. Notice that this is the same equation that we used previously, just rearranged for Q. And so now we're going to go ahead and sub in for what we have here. So we have, this is going to be C equivalent for what the battery is going to see, all three of them combined. And that's going to be the voltage of the battery. C1 times V, and actually these are all going to be the same V, right? So the V's should divide out. And that's because we have the same voltage because of loop rule. And so from here you can see then that this shows where we get the equivalent capacitance for capacitors in a series. And this, just like we saw with the previous series relationship, is similar to resistors, but for the opposite, right? Meaning that parallel capacitors have the same mathematical equation as series resistors, right? So again, the capacitor equivalent equations are going to be the opposite of the resistor ones. All right, I hope this helps, and we'll take a look at more problems in class. Thanks.